Time is this deeply personal thing, but it's also this universal mystery, right? So in this explainer, we're going to dive into a really fascinating simulation that doesn't just clock time. It actually tries to model the feeling of time passing. Let's see how it works.
I mean, we've all been there, haven't we? That amazing week-long vacation just vanishes in what feels like a blink of an eye. But a single dull hour stuck in a meeting can drag on forever. The clock on the wall is telling you one thing, but the clock inside your head is on a completely different planet. How do you even begin to model something like that?
Okay, so to get our heads around this, we're going to look at a simulation that totally rethinks what time even is. Forget the constant, ticking metronome. Here, time is something that's actually generated by a mind as it takes in new information. It's a world where your experience literally creates its own timeline.
So, if our minds are generating time, what's the engine? What makes it go? Well, the core idea here, the fundamental principle of this simulation, is that our internal clock is really driven by one thing: surprise. Or, to put a finer point on it, entropy. Let's dig into the architecture.
The way this simulation works is pretty clever. It actually breaks time down into 3 different layers. First, you've got proper time. That's tau. Think of it like the universe's stopwatch, the objective physical tick-tock that nobody can argue with. Then there's block time, which is the environment's own timeline. But the real star of the show for us is GUI time, or t-hat. This is the time that the observer actually feels.
And yeah, this is where things get super interesting. GUI time isn't measured, it's made, it's generated. And what generates it? The process of learning. When the observer runs into something new, something surprising, what the model calls a high-entropy event, its internal clock kicks into high gear. But when everything is predictable and same old, that clock slows right down to a crawl.
There's a quote from the source material that just hits the nail on the head. Learning becomes a temporal actuator. What that really means is that the act of updating your worldview, of learning something new, is the very thing that pushes the hands on your internal clock forward. Learning doesn't just happen in time. In a way, it creates our experience of it.
And wow, check this out. This data log shows it perfectly. Look at the physical clock, tau, in that first column. It's just ticking along steady as a rock, 0.008, 0.016. But then look at t-hat, our subjective time. As soon as a high entropy event hits, bam, it jumps massively. At step 25, another surprise hits, and it leaps again. In just a fraction of a physical second, the observer experienced a huge amount of subjective time, all because its world suddenly got unpredictable.
All right, so we've got the basics down for a single mind generating time. But what happens when you throw another person into the mix? What happens when you have 2 observers, each with their own unique point of view? Well, this is where it gets really mind-bending.
So now, let's level up the simulation. We've got 2 independent observers, let's call them A and B. They're moving through the exact same world, but since they're in different spots and have different internal models, their experiences, and crucially, their perceptions of time are going to be completely different.
Now, to make things more realistic, each observer has 2 internal clocks. Think of the fast clock like your gut reaction. It's for raw sensory data, that split-second, whoa, what was that feeling? Then you've got the slow clock. That's more like your long-term, stable worldview. It's got inertia. It doesn't just change on a whim. It's the difference between jumping at a loud noise and slowly, over time, realizing the building isn't safe.
Okay, but here's the real kicker, the part that connects everything. This is not a one-way street. When an observer gets hit with a huge surprise, that cognitive shock doesn't just stay inside their head. In this simulation, there's a feedback loop where that mental chaos actually injects noise and turbulence back into the environment. Their surprise literally makes the world around them more chaotic for everyone. So, that brings us to maybe the wildest, most advanced part of this whole simulation. What does a mind do when it's hit with a shock so big it just shatters its whole understanding of the world? It doesn't just adjust its beliefs. It does something much more radical. It branches.
It's a process called memory branching. When some crazy high-entropy event happens that completely contradicts what the observer thought was true, the mind doesn't just throw out the old theory and pick a new one. No, instead, it's like its memory sprouts these different branches, exploring multiple competing versions of reality, multiple what-ifs, all at the same time. It's a survival move, really. So you can almost picture the life cycle of a belief here, right? You start with a nice, stable worldview. Then, wham, a huge shock hits. Your mind kind of fractures, sprouting all these new possible explanations. And as more information comes in, the possibilities that don't make sense get pruned away, until only the strongest, best adapted belief is left. It's like cognitive evolution, but happening in hyperspeed. Okay, so let's put it all together. The whole shebang. You've got two observers, each with a fast and slow clock. They're feeding their own surprise back into the world, making it more chaotic. And when they get shocked, their memories branch out into new possibilities. So, when you run that simulation, what does the final result actually look like?
What comes out the other end is, well, it's pretty extraordinary. It's a wild demonstration of just how much our inner world can warp the experience of time. We're about to see how huge the gap can get between a physical clock and what an observer actually lives through.
Okay, get ready for this, because the final numbers are just mind-blowing. Look at the data for observer A. The physical time that actually passed, tau A, was just over 1.5 seconds. That's it, barely enough time to blink. But now, look at the subjective time generated by its fast sensory clock. 52.33. Let that sink in for a second. In the time it takes to snap your fingers a couple of times, this observer lived through what felt like over 52 units of experience. That is a massive, massive expansion of subjective reality.
And I mean, this chart just says it all, doesn't it? That tiny little bar on the left, that's the objective, physical time that passed. And that massive bar on the right, that's the amount of time the observer actually felt. This right here, this is your lightning-fast vacation week next to that painfully slow hour in a waiting room, but spelled out in hard data.
So what are the big takeaways here? What is this all telling us? It's showing us that our minds and the world aren't separate things. They're locked in this crazy feedback loop. It's suggesting that every single one of us is living on our own unique timeline. And it paints a picture of consciousness not as some passive camera recording the world, but as an active player, constantly branching and evolving to make sense of the chaos.
So this entire model basically anchors our personal experience of time to learning, to surprise, to novelty. And that leaves us with a really deep question to chew on. If a predictable, routine life literally slows down our internal clock, what's the real cost, measured in the richness of felt time, of a life lived without surprise?